All right, everyone. Let's have a simple and fun chat about something you experience every day, but probably never thought much about. How heat moves in air and water when it's flowing. Imagine you are outside on a hot day and the wind blows. Suddenly you feel cooler. Or imagine you blow on your hot soup and it cools faster. Why does this happen? This is what we call convection. And today, we are going to learn how it works in a way that's easy to picture, like a story. When we heat something, like a cup of tea, the heat moves inside it. Sometimes, heat moves because the hot side just passes heat to the cold side, like how your hand gets warm when you touch something hot. That's called conduction. But if the air or water itself is moving, like the wind or a fan, it carries the heat along. That's convection. Heat hitching a ride on moving air or water. Convection happens in two ways. First is forced convection, where you have something like a fan or a pump pushing the fluid to move. Second is natural convection, where heat causes movement by itself, like how warm air rises because it's lighter and cold air sinks because it's heavier. When convection happens, it creates something like invisible layers. Near the hot surface, the air doesn't move much, and heat sneaks through by conduction. But a little bit away, the air starts to move and carries heat faster, making convection happen. Engineers like to use a simple rule called Newton's law of cooling, which basically says that the hotter something is compared to the air around it, the faster it loses heat. But here's a fun trick. The way fluid moves near a wall or surface changes everything. Right at the surface, the air sticks to the wall like glue and doesn't move at all. This is called the no-slip condition. It's why the air right on your skin or on your soup surface doesn't move even when there's wind above it. Because of this, heat moves by conduction right at the surface, but by convection a little farther away. To make life easier, we use something called the Nusselt number, which is like a scorecard, telling us how much faster heat is moving because of convection compared to just conduction. The higher the score, the more powerful the heat transfer. When you blow on your soup, you're actually increasing that score. Fluid flows can be very different. Sometimes the flow is calm and smooth, like syrup flowing slowly, which we call laminar flow. Other times it's wild and messy, like river rapids, which is called turbulent flow. When you blow on your tea gently, it's laminar. When you blow hard, it becomes turbulent and your tea cools much faster. There are a few more cool tools we use, like the Reynolds number, which tells us if the flow will stay calm or become turbulent. There's also the Prandtl number, which tells us how quickly heat moves compared to how quickly the fluid moves. Different fluids have different behaviors. Water, air, and oil all have different ways of moving heat. Then we learn about the boundary layer. This is like a special invisible blanket near the surface. The fluid sticks to the wall, then slowly speeds up as you go away from the wall. This area is called the velocity boundary layer. There's also a thermal boundary layer, which shows how temperature changes from the hot surface into the cooler fluid. These layers tell us where the action happens, where heat is fighting to escape. And don't forget, when fluids flow inside pipes or ducts, it's called internal flow. When they flow over a surface, like wind blowing on your face, it's external flow. Engineers need to know whether we are dealing with internal or external flow because it changes the way heat moves. In the end, we use all these ideas to design things around you: air conditioners, radiators, car engines, and even your laptop's cooling fan. By understanding how air or water moves heat, we make sure things don't get too hot or too cold and stay comfortable to use. So next time you feel a breeze, blow on hot food, or turn on a fan, you'll know it's not just air moving, it's heat moving, too, faster and smarter, thanks to convection. And now you understand how to explain it just like an engineer would, but in the fun way we talked about today.